Okay, so last day we had considered, or in the last couple of days or lectures, we had considered comparing means, and we can do that for paired experiments using a paired t-test, or if we have independent samples, in other words, there is no pairing, and we have two groups, we can compare the means using a two-sample or independent sample t-test. And while we were doing that, we also discussed the assumptions of those two tests. So if those assumptions fail, so the assumptions for paired t are that the distribution of differences are normally distributed. There are two assumptions for the unpaired or independent sample t-test, and they are that the populations sampled are normally distributed for whatever the trait, or the trait measured is normally distributed, and that the variances of that trait in the two populations, or in the two groups, are also the same. And then we went on and did an F-test, which was a test that you can use to compare variances, and so you can actually test that assumption, ask whether or not the variances are different. If they are different, then you really have violated the assumptions of that t-test, and technically you shouldn't conduct it because the conclusions you draw could be wrong. And we kind of left off there. And so the issue now is, what if you violate the assumptions? What do you do? And so this is the subject matter of chapter 13, and we'll cover a number of portions of chapter 13. You can see the course outline to know which sections, etc., we might not consider of chapter 13. So let's move on. And so what if we violate the assumptions of normality? And what if the variances are different? What do we do? So again, we're talking about numerical data, and we need to handle it in some way. So I would argue that the first thing to do, and the first thing that I typically do, is to transform the raw data. Okay, so if you wanted to do a t-test, paired or unpaired, and you violated the normality assumption, or the variances are different, you can do a data transformation. And there are a number of different data transformations, and I'll cover some of them. And one of the issues with data transformations is you don't necessarily know which ones to use and which ones are going to be effective. So by data transformation, I mean you take every raw data point and you use exactly the same mathematical operation on that data point, and then you can see whether or not you've met the assumptions, whether or not the data, for example, are now normally distributed. So I'll go over some commonly used data transformations. And so let's imagine that you have some data. Imagine it's height data. You measure the height of individuals or of a plant species. You measure how tall it is. And you plot that data. So you plot a histogram. So here's my sort of representation of what a histogram might be for heights. So this is frequency on this axis. I've drawn it as a smooth curve. It would obviously be a histogram if you had real data. And this is height of a plant or animal or something. And so you plot the data, and you can clearly see that, at least from a pictorial perspective, if you have a decent sample size, it's not normally distributed. Right? This is, if you remember way back when, looking at distributions, this is skewed to the right. If data are skewed to the right, there's a transformation that commonly works, but there's no guarantee, and that is if you take the log, either the log base 10, so log of base 10, or the natural log of every data point, and then plot those. So if I were to do that, that would often, so this might be now the logarithm of height. If you do that often, this makes the distribution somewhat or approximately normally distributed. As I said, there's no guarantee this will happen, but this is often a transformation that works. Where you have data, where you plot the raw data, and you observe a skewed distribution, if you take the log or the natural log, it doesn't really matter which, often that will make the data normally distributed. And then what you do is you do your t-test on those log transformed data. So that's a very effective method of dealing with lack of, when you fail to meet assumptions. As I said, there's no guarantee things will work, but there are some clues. So if I see a distribution skewed to the right, I'll try a log transformation. And note that in some cases, sometimes instead of doing just a log transformation, let's pretend for the moment that the variable we're measuring, we'll call it x. X for height, we have a bunch of heights, or whatever they are, whatever the units are. If you have negative numbers, or even zeros, that log transformation is going to fail, right? Because you can't take the log of a negative number. And so what you need to do is to add typically a small constant to the data. So instead of just going log of x or natural log of x, you might do something like log of x plus some small constants. So let's imagine in your data you had, some numbers that were 0 or maybe, minus 0.5. You might then just add, 1 to every value and then take the log of it. Right? So you add the same constant is added to every value, then you take the natural log or log of base 10. So that's how you can deal with those. I should also add that if you were comparing means, and later on in another lecture, we'll compare the means of more than 2 groups. So let's imagine we want to compare the means of 5 groups. And so what I'm going to do is I'm going to plot the means of each of the 5 groups along this axis. So this is 0, whatever these numbers, 2, 3, 4, for some variable we're measuring. And I'm also going to plot the standard deviation of each group here, whatever these values are, 0.1, 0.2, 0.3, 0.4. So I'm going to compare, let's say, 5 groups. I'm going to calculate the mean of each of those groups, and I'm going to calculate the standard deviation. If you plot those, so let's pretend there's one here, group 2 is over here, group 3 is here, group 4 and group 5. If you plot the standard deviation against the means, and you see an increasing relationship, it doesn't have to be perfectly linear, but if standard deviation increases as the mean increases, that also suggests that a log transformation will be effective at removing non-normality and or the variance heterogeneity, right? In a plot like this, where I'm plotting means against standard deviations, you can see that the variances, although I've plotted these as standard deviations, the square root of variance, the variance increases, right? And so it's very likely in this case that these populations differ in variance, although you'd have to formally do a statistical test for that. If you have a scenario that looks like this, taking the log again of each raw value has the tendency to make the variances or the standard deviations the same. So that's one thing you can do. That's log transformations. Another transformation that works under the same circumstances often is to take the square root, do a square root transformation. To take the square root of every variable. That tends also to work if you have, right, a skewed distribution of values. Right? It's not normally distributed, it's skewed to the right. Positive skew, skewed to the right. You could take the square root of each number. That also may be effective. And as I said, there's never any guarantee it's going to work. Clearly, if you're doing these on computer, it's easy, right? In SAS, you have the code to do that. You can enter your raw data in SAS, use proc univariate to ask for a histogram. So look up that code, look at its distribution. If it's not normally distributed and skewed to the right, you can then easily tell SAS, remember you can do arithmetic operations in SAS to easily convert every value by taking its square root, or taking its log, or taking its log plus some small number, etc. You can then look at the distribution. So real easy to do on computer, very tedious to do by hand, in part because there's no guarantee any transformation is going to work. In other words, make the data more normally distributed or make the variances similar to each other, not different from each other. Doing it by hand, you might have to run through a number of different transformations. It would be very tedious. So ultimately, you want to do these on computer. And these are some clues as to what might work under certain circumstances. So I'll just teach you a few of these transformations that tend to work. So what if you're analyzing percentage data? So there's a transformation, has a couple of names. One name is the arc sine transformation. And it's commonly applied to proportions. So if your data are proportions or percentages, you simply convert your percentages to proportions and then use this transformation. And so this transformation, where the data are composed of percentages which you can convert to proportions. So we'll use the little symbol p to represent the proportion. So here, an example that is often appropriate is grades of students' grades and percent grades in a course, right? You get 86.5% or whatever you got. You convert that to a proportion 0.865. So we have a bunch of student grades. Let's say we wanted to compare the performance in a particular course from one year to the next. So we convert everybody's grade to a proportion, and then we can do a t-test on proportions. So p are the proportions, but the transformation is, I'll just call it p trans, where the transformation is to take the arc sine, or the inverse sine of the square root of each proportion. So first you take the square root of each proportion, then you take the inverse sine. And this transformation tends to make proportion data normally distributed. Now and sometimes, if you look at the literature, people will, if they have proportion data they want to compare, they will, even without looking at the raw data, in other words, plotting it and seeing if it's normally distributed, they will automatically apply this particular transformation. It's sometimes called an angular transformation. So this one often, but again there's no guarantee, often works to make the data normally distributed if you're dealing with proportions. And one of the problems with proportions are the following. Let's imagine you have a really bright class one year, brilliant students, so they're taking basket weaving 100, and it's a brilliant group in this year. And so what happens is, here's a graph of what the data might look like. Here's 0%, here's 100%. These are the grades, and you're going to plot a frequency distribution, a histogram. And so what happens if you're a brilliant class, I'm just going to put a bar here, is it all crashes up against 100%, right? You can't get better than 100%. So this ends up being skewed because they're so, right? You'd like, for a normal distribution, people would have to, get scores better than 100%, but you can't. So it crashes into 100%, and you can't get above 100%, and so you get a very skewed, right? This is skewed left. And imagine another scenario where they aren't brilliant. It's, slow, to be polite. This class is not very good this year. Different class, different year. And they all crash up against 0%, right? They're not, and so now you get a distribution that's skewed to the right, a positive skew. It's not normally distributed. So it turns out that the arc sine transformation has the effect of being able to force either of these two scenarios, crashing into 100% or crashing into 0. It forces these to be normally distributed or more normally distributed. I mean, if it's very extreme, nothing's going to work. As I said, there's never a guarantee these things are going to work. But and you don't typically have a class that has distributions like this, where a huge proportion get 100% and many fewer get lesser percent, or where there's a huge number that get 0%. You typically have some intermediate state, which this transformation is effective at improving the normality of. So that's a transformation that is commonly applied, and you should know how to apply it. So those are the only two I'll really talk about: the log and arc sine the log transformation or the square root transformation, And then for percentages, which you need to convert to proportions first before you analyze them. Right, so P is a proportion. And if you have a percent divided by 100, then it's a proportion. And then away you go. Take the square root, take the arc sine, and you then analyze those data. And this is all easily done on SAS. In fact, if you look at the website, I have put up a PDF, or maybe I can't remember if it's a Word document that describes those transformations. So you can find those if you look at the course outline on the website. So commonly applied, some potentially useful operations in SAS, I think it's what it's called. Okay, so let's move on. So that's, as I said, this is the first step. You're going to do a t-test or a paired t-test. You don't meet the assumptions. You can apply one of these transformations, especially for unpaired or independent sample t-tests. And later on, when we're comparing more than two means, you can likewise try to use these and see if they work. So you want to apply the transformation to every raw data point, then see if you meet the assumptions of normality, and see whether or not the variances are still different or not. And hopefully the transformation works, and then you can happily carry out the t-test that you wanted to carry out. All right, so what if and I said there's never a guarantee these will work. What if it doesn't work? What do you do then? And so what you do then depends on which test you're doing. There are a number of tests that are collectively known as nonparametric tests. And these tests have fewer assumptions than do the tests we've considered, the t-tests. And so you can use one of these tests in place of a t-test. So the downside of nonparametric tests is they are less powerful than the corresponding t-test would be called parametric tests. So they're less powerful, so you don't want to automatically use them. You only want to use them if you need to. So if you violate the assumptions and you can't find a transformation, then you use a nonparametric test, because at least the results of these tests will be correct. If you use a t-test where you violate the assumptions, you may draw an incorrect conclusion. So you want to jump to a nonparametric test. So let's first consider how to deal with a paired t-test. So remember, in a paired t-test, data are paired before an experiment, and then you assign the treatment to one individual of each pair, and then the other one might serve as a control. You subtract the values, and then you operate on the differences. So let's do an example where we want to compare the growth of plants that are treated with auxin. Okay, so auxin is a plant hormone. It has an effect on plant growth. And so we're going to conduct an experiment where we're going to match plants according to their starting heights, and then apply auxin to one, and the other is a control. It doesn't get any auxin, and then after some period of time, we're going to measure the height of that plant. We're starting with seedlings, let's say. And so the null hypothesis here is, I'm just going to write it out in words. It could be written in as if it was means, for example. But I'll just write it in words. So auxin doesn't change leaf length. And the alternate hypothesis, it'll be two-sided. Auxin does change leaf length. So there's no specification by the experimenter as to directionality. So this is a two-sided test. Okay, so now I'll give you the data. So they match up plants, seedlings initially by size. One gets auxin, one doesn't, and they measure it. So here, here's the particular pair of plants, pair 1, 2, 3, and so on. Here's the measured leaf length when you apply auxin. Whoops. There's an I in there. Here's the control value. Here are the differences. And I'm going to leave another column that I'm going to add later on. So pair 1, 2, 3, 4, 5, 6, 7, and 8. The auxin value, so the individual that got the auxin grew 100 centimeters. The control for that pair only grew 6. 19, 16, 12, 15, 3, 4, 60, and 4, 8 and 3, 20 and 2, 20 and 18, 9 and 2. So that's the data, and this is really set up as if it's a paired t-test. And so really you'd like to analyze it as a paired t-test because you have matched subjects. So you want to calculate the differences. So this is 94, 3, -3, -1, 56, 5, 2, 7. And so if you recall, the assumption of a paired t-test is that the differences are normally distributed. And so ideally, and you can plunk these into SAS, run it on proc univariate, see whether or not these data fall into a normal distribution. Now there are too few data here, obviously, to do anything with it along those lines. And if you're sitting there writing a test, you also can't easily test for normality. So instead, what I'd like you to do is, if you're going to do a paired t-test, proceed as if you're going to, in other words, calculate the differences, and then simply look for outliers. Just look for observations that are way out there relative to where most of them are. And so in this data, we can see most of the differences lie between -3 and 7. And then we got two very huge values. These are outliers. If they're outliers, that's going to violate the assumptions of normality, right? This is going to be extremely skewed, even without plotting anything. You can see it's going to be extremely skewed to the right. So that's going to violate the assumptions. And so instead what we're going to do is we're going to do what's called a sign test. So instead of analyzing the differences, we're going to analyze the sign of the differences. So I'm going to add this column. It's going to simply be the sign of the differences. So in other words, whether they're positive or negative. So that's positive, positive, negative, negative, positive, 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 positive. So now what we're going to do, when we violated that assumption of the normal distribution of differences, is a sign test. We're going to analyze these signs. And effectively what this reduces down to, the sign test really is a binomial test. If you can remember back to that. We're going to end up doing a binomial test. So for example, let's look back at our null hypothesis. It says auxin doesn't change leaf length. And so really you'd expect on average, if that's true, the differences would add up to 0. If we talk about signs, we'd expect as many positive signs as negative signs. Right? That'd be the proportion of positive signs should be p equals 0.5, if in fact auxin has no effect. And so what we can do is we can test whether or not having 2 negative signs out of 8 observations, we can calculate the p-value. What's the probability of getting 2 negative signs out of 8 if in fact there should be half of each, half negative, half positive. So this really becomes a sign test. Sorry, a binomial test. And so let me set that up as if it's a binomial test. So in some respects, what the null hypothesis now could be rewritten as p equals 0.5, right? Proportion of positive signs is 0.5. Or if you wanted to, you could have p as the proportion of negative signs is 0.5. Or you could say the proportion of positive signs equals the proportion of negative signs. And the alternate hypothesis could be p doesn't equal 0.5. Remember, this is a two-sided test. And so now we're going to do a binomial test, right? So you're going to haul out your equation for the binomial distribution. And so if you can remember back to that, what we want to do in this case is we want to know the probability of getting 2 out of 8, 1 out of 8, or 0 out of 8 negative signs, if indeed it's true that p equals 0.5. So we're going to plug things into the equation for a binomial distribution. And so if we do that, what's the probability of getting x equals 2 negative signs given that p is 0.5? So that's, and remember n is 8. We had 8 paired samples, so n is 8. P is 0.5 as specified in the null hypothesis. So this is 8 factorial over 6 factorial, 2 factorial, 0.5 to the number to 6, and 0.5 to the 2. So you need to calculate that out. What's the probability of getting just one negative sign given that p is 0.5? This is 8 factorial, 7 factorial, 1 factorial, 0.5 to the 7, 0.5 to the 1. And finally, the probability of getting no negatives, 8 factorial over 8 factorial, 0 factorial, 0.5 to the 8, 0.5 to the 0. And so if you calculate those out, this is 0.1094, 0.03125, 0.0039. And so remember, to get the p-value, we want to sum those. So first we're summing. So what does that mess add up to? 0.1445. It's a two-sided test, so we need to multiply that by 2 to get the p-value because it's a two-sided test. So the p-value here is 2 times 0.1445 or 0.289. So that's the p-value. This is the probability of getting a result as extreme or more extreme than one we obtained. In other words, only 2 negative signs out of 8, 1 negative sign, 0 negative signs, given that the probability or the proportion of those should be 0.5. So the p-value is quite high, right? The p-value is a fair bit bigger than 0.05. So we don't reject the null hypothesis. Right? We've got no evidence that plants given auxin grow bigger than those that don't get the auxin. So we have to jump way back to the original hypothesis about plant growth, although what we ended up analyzing here were, right, we converted to differences, then we converted those to the sign, and then we achieved the answer. Likewise, so this, as I said, was you set up as if you're going to do a paired t-test. So if you have data for a paired t-test, you set it up as if you're going to do it. That's the test you really want to do. It's a more powerful test. Calculate the differences and look at them. If it turns out that you see some really big outliers, that's a violation of normality. So instead, set up another column where you simply write the sign of the difference, whether it's positive or negative. Then you're going to analyze the signs using what is effectively a binomial test. Right? You typically are going to expect an equal number of plus and minus signs, so you're going to do a binomial test. P is going to be 0.5. Haul out your equation for a binomial distribution and calculate the probability of getting a result as extreme or more extreme than the one you obtained. I followed minus signs, what's the probability of getting 2 minus signs, only 1, only 0? You get exactly the same result if you said, what's the probability of getting 6 plus signs, or more extreme, 7 plus signs, 8 plus signs. You would get exactly the same result. So we did a two-sided one. If the original hypothesis, alternative hypothesis was one-sided, you wouldn't multiply. You do the same approach, simply don't multiply by 2 to get the p-value. You just sum up those binomial probabilities. Okay, so that's how we deal with, how I'd like you to deal with data that should be analyzed as a paired t-test. You set up, you want to do the paired t, look at the distribution of differences. If you see outliers, and if I give you examples like this, I'll make the outliers really big so they'll be sticking out. Do a sign test. It's a nonparametric test. It's not as powerful as a paired t-test. And you can kind of see why that is, because you lose information. When I convert the number 94 to a plus sign, right, 94 is a huge number, but it's just a plus sign. The value 3 is a kind of a tiny difference. It's weighted in the same way. So you're losing information when you jump to this. But if you violate the assumptions, the analysis using a paired t could be meaningless. So that's why you need to do the sign test. Or let's now move on, and we'll do another non-parametric test. And this time, it's a test that you're going to use if you violate the assumptions of an independent sample or two-sample t-test. It's called the Mann-Whitney test or the Mann-Whitney U test. It has a few slightly different names. And so again, what I'd like you to do here is, if you have data for an independent sample t-test, two-sample t-test, you want to compare two means. The data are not paired. So that's the test you want to do. But the first thing you're going to do, remember, is first do an f-test to test whether or not you meet the assumption that the variances are the same. This is sometimes called a homogeneity of variance test, right? Do that f-test first. If you don't reject this null hypothesis, you happily do the two-sample t-test. If you reject the null hypothesis, in other words, if the variances are different, then what I'd like you to do is the Mann-Whitney U test. Okay, so let's go over a Mann-Whitney U test. So a Mann-Whitney U test is another non-parametric test. And effectively what it does, it acts like there's a number of tests, so we're not going to talk about many of the non-parametric tests. In many ways, the same principles apply as those that we're going to do here in the Mann-Whitney U. And what ends up happening in the Mann-Whitney U test is, instead of analyzing the raw data, you analyze the ranks of the data. So the data are effectively first ranked from small to large, and then instead of analyzing the actual measurements, you analyze the ranks. Incidentally, sometimes you don't have raw data. Sometimes data are originally composed of ranks. In other words, instead of measuring the height of people in a class, what we could do is we can just take a random sample of people in the class and just visibly line them up from smallest to largest, and the smallest person gets a rank of 1, the next bigger person gets a 2, the next person who's bigger gets a 3, and so on up to whatever. Those are ranks. The ranks could be analyzed. So sometimes you actually don't collect data, you collect ranks. If you have ranks, you simply jump immediately to a Mann-Whitney U test. Okay, so let me give an example of one of these. And so what we want to do, here's an experiment. It's easiest to follow this if we're doing an experiment. So let's imagine someone is carrying on an experiment where they want to compare the size of bracket fungi. Bracket fungi are those big white fungi that sit on the trunks of trees. They look like brackets. And you want to compare them in two forests. So you're going to randomly sample forest 1 and forest 2, measuring a number of trees in them, measuring the size of the bracket fungi. So let's imagine that's what we were going to do. And you've got this raw data on measurements, and you do an F-test, and you find out the variances are different. So the variance of one group is different from the other. And you can't find any transformation of the data that makes the variances similar. They're still different. Then you're going to do a Mann-Whitney U-test. So I'm just going to write out the null hypothesis in words, although it could be written as if it was means. So I'm going to say the size of fungi is the same in both forests. And the alternative hypothesis is going to be the sizes are not the same. And so this is clearly a two-sided test. We really would like to have done a two-sided, it's a two-sample t-test that's two-sided. But I've gone through the motions of testing the assumptions, and I violate the assumptions. I can't find a transformation. So instead I'm going to do a Mann-Whitney U-test. So let's move to, I'll use another page because I'm going to write a data table down here. And so what we've got here is forest 1. Leave a space here because I'm going to add ranks for forest 1. I've got forest 2, or fungi from forest 2, and then the ranks of those. And the sample size in this experiment turns out to be equal. The sample sizes don't have to be equal, but as always, it makes most sense to have equal sample sizes. So N1, the sample size for forest 1, is 8, and likewise N2, the sample size for forest 2, is 8. All right, so now I'm going to write down the sizes of brackets, the lengths or widths of the bracket fungi in each tree. So the first one had 30 centimeters, 29, 24, 20, 31, 42, 38, 24. Forest 2, the first fungus was 40, 26, 23, 10, 21, 18, 31, 20. So I'm going to leave some space under here because we need to come back and add some stuff later. So the first thing you do when you're doing, as I said, we know that we can't do a t-test, a two-sample t-test, which is what we'd like to do because it's more powerful. We violated the assumptions. So the first thing you need to do is to throw all the data together and rank them from smallest value to largest. Throw all the data together. Rank from small to largest. All right, so tedious to do by hand. That's why you want to learn how to use SAS to do all this stuff. Even with just 8 samples in each forest, that's 16 numbers, you go through the pain of ranking them. So here we go. So I'm going to write down the raw data, ranked, and below it I'm going to write in the ranks. So here we go. The smallest number looking at both forests is 10, then 18, then there's a 20 in forest 1. Here we go. And there's also a 20 in forest 2. So I'm going to write the number 20 down twice. There's a 21, 23, 24, 24, because there are 2 of them. There's a 26, 29, 30, 31, 31, 38, 40, and 42. So those are all the data. There should be 16 values. All of them ranking them from smallest to largest. Then the next thing you do is kind of easy. You just assign a rank. So the smallest one gets a rank of 1, 2, 3. So just write consecutive numbers starting from 1 all the way up to whatever the total sample size was. In this case, it's 16. So 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So there we go. We've got the ranks assigned now. Finally, what you need to do is you need to look at the ranks, and if there are any ties, if there are any values that are the same. So here we have two 20s. So it doesn't make sense to give the rank 3 to one of the 20s and the rank 4. So instead, when you have tied ranks, each one gets the average of the ranks of each one. So this number 3 gets replaced by 3 plus 4 over 2, which is 3.5. And the same for that one. So these numbers both become 3.5. It's the average rank of those two tied values. Likewise here, there are two 24s, so they get the average of 7 and 8. So it's 7.5 for this one, 7.5 for that one. Are there any other ties? Yep, two 31s, so 12.5 and 12.5, and those are the only ties. If you had three tied values, you take the average of the three values, and each of those three numbers would get the average of those three ranks. So that's pretty straightforward, but tedious, right? Imagine this is a small data set. Imagine if you had a larger data set. Just the act of ranking the data by hand would be tediously painful, and then you'd have to look for tied ranks. Ideal to learn how to do this on computer. And there's info for that in the problem sets, how to do these by computer. Okay, so now what we do is we go back to our original data table at the top of this page and write the ranks in. So the value 30, so look for 30, here it is. The rank of 30 is 11, so I'm going to write an 11 here. The rank for the next number, 29, is 10, so I put a 10 here, and so on. So beside each of the raw measured values, I'm writing in the ranks. So this gets a 7.5, 3.5, 12.5, 16, 14, 7.5. Then for forest 2, write in the ranks there as well. So 40 has a rank of 15, then 9, 6, 1, 5, 2, 12.5, and 3.5. So there we are. We've spent a fair bit of time doing this ranking and assigning ranks. And so now what happens in this test is all the operations are carried out on the ranks. So we ignore the raw data we've collected for now, and we're going to operate on the ranks. And so there's a couple of things we need. We've got the sample sizes of each. They happen to be equal. They don't have to be. We want the sum of the ranks for each of the forests. So the sum of the ranks for forest 1, we'll call it R1. You just add that column together. So what's the sum of that stuff? That ended up being 82. And then we want R2, the sum of the ranks for forest 2, and if you add up these numbers, they come out to 54. So now we've got some of the values we need. The next thing we need to do is we need to calculate the Mann-Whitney U statistics. And so when you're doing a two-sided test, there are two U statistics given by this equation. They're called U1 and U2. So here we go. Here's the U1, or I might call it U1 calc. It's the U1 statistic. It's N1 times N2 plus N1 times N1 plus 1 divided by 2 minus R1. R1, remember, is the sum of the ranks for group 1. So that's one of the U statistics you need to calculate. And so let's do that now. So for this example, we've got 8 times 8 minus 8 times 9 over 2 minus the sum of the ranks, which is 82. And so the U1 statistic equals 18. So that's the first thing we need to calculate. Then we need to do the U2 statistic as well. So U2 is really a similar equation. It's N2 times N1 minus n2 times n2 plus 1 over 2 minus r2. So it's the analogous equation to the u1, and we're going to calculate that value. So u2 in our case equals 8 times 8 minus 8 times 9 over 2 minus 54. And so the u2 value equals 46. So now we've got two U statistics calculated, and so you always calculate two U statistics when you have a two-sided test. So you're going to calculate U1 and U2, but then what you're going to do is you take whichever of these is larger, take the larger U statistic, and that is your test statistic. Or let's call it ucalc. So which is larger? U1 was 18, so that's not it. U2 is 46, that's the one we want. So ucalc, the test statistic in this case, equals 46. That's the test statistic we're going to do. And so what we really want to know now is this if those fungi are the same, remember our null hypothesis was that the size of the bracket fungi was the same in the two forests. If that's true, is this an unusually large U statistic? Or is it, if it's unusually large, you want to reject the null hypothesis? And so what we need to do now, not surprisingly, is refer to the Mann-Whitney U tables. So there are more statistical tables to look at. The Mann-Whitney U tables. To look up the critical value, we want the critical value of U. And in this case, we don't, with sample sizes, so we don't call these degrees of freedom, they're simply sample sizes. So we want to look up a critical U value with N1 equal 8, with N2 equal 8, at alpha 2 equal 0.05. So in the textbook, there are U tables. I think one table is for alpha 2 equaling 0.05. The other table, I think, is for alpha 1 equal 0.05. And you're just going to look up critical values. And if you do that in this case, and I'll show you how to deal with those tables later, the critical value ends up being 51. And so I don't know the exact shape of the Mann-Whitney U distribution, but let's pretend it has a shape something like this. Here's 0. It turns out that the Mann-Whitney U distribution, the lowest value is 0. The maximum value is N1 times N2, so it ends up being 64. So let's pretend, as I said, it doesn't really matter what the shape is. Let's pretend the shape kind of looks like this. And so what we're doing here is we're setting up rejection region out here. Because we picked the larger of the two, we're kind of always looking out at the positive end of this distribution, or the bigger end of the distribution. So all alpha 0.05 is sitting over here. And we looked up the critical value, and it was 51. So that's right. Our test statistic, ucalc, equaled, what was it? It was 46. It sits over here somewhere, so we don't reject the null hypothesis. No evidence fungi in the two forests differ in size. Okay, and I think I'll stop there, and the next lecture will continue and do a one sample test, and one sample test where you really want to do sorry, not a one sample test. We'll do a test where you want to compare two means again, but you violated the assumptions, and it's a one-sided t-test. So we'll do an example of how you do a Mann-Whitney that's just one-sided. And I'll also show you how to look up information in the tables for the Mann-Whitney U distribution.